Hello. Last time we were talking about Newton's laws of motion. And then we ended talking about Newton looking up at the moon and thinking that possibly maybe the same thing, the same force that makes an apple or something fall on Earth is the same force that's responsible for keeping the moon going around the Earth. And so this, it is said, led to gravity. So what we're going to talk about today is Newton's law of gravity and actually see how gravity works. So to do that, I'm going to write down this law of gravity. It's quite a paragraph. So let's write down Newton's law of gravity. And then we'll write it down as far as in kind of an equation, and you'll see that an equation makes it much easier. So the law of gravity says this: between any two masses in the universe, there is a force of attraction called gravity, which he called gravity, which is directly proportional to the product of the masses and is inversely proportional to the square I think there should be E there. Inversely. That's right, ELI. And inversely proportional to the square of the separation between the centers of the masses. I told you. All right, I'll read it again to you. Between any two masses in the universe, there is a force of attraction called gravity, which is directly proportional to the product of the masses and is inversely proportional to the square of the separation between the centers of the masses. Now, let's make this a little more simplified. First of all, let's take a look in here, what we're going to pull out. Well, let's talk about this force of attraction called gravity. The force of gravity, all right? Force of gravity. And let's put that over here. All right, let's call the force of gravity F sub G. All right, there's the proportional symbol, so we'll do that. It's directly proportional to the product of the masses. You know what that means? It's directly proportional to mass 1, and then times product times mass 2. Two masses, we'll show that. And is inversely proportional, so there's the product of the masses we just wrote down, and is inversely proportional just means over the square of the separation between the centers of the masses. So the square of the separation. So we're going to say distance between them squared. So let's see how this works. Let's see how this works with Earth. So with Earth, because we have the force of gravity on us, being on Earth, so let's show Earth. So here is Earth. And let's put us on Earth. Let's say here, that's you. That is you, standing on Earth. So let's say you want to figure out the force of gravity on you. And here's all you have to do. You'd have to figure out your mass, mass 1, which we can say mass 1 is you, mass 1. And the mass, remember, mass is just how much stuff you have, mass 1. What would be mass 2 here? Earth, mass 2. Then you multiply them. Mass 1 times mass 2 divided by the distance between the centers, which is pretty much from the surface of the Earth, the center of you to the center of the Earth. The distance will say squared. That's it. All you need are those variables. And now, I know a lot of times you're used to having an equal sign. So in reality, the force of gravity equals, if you can do it this way, G, mass 1, mass 2 over distance squared. So you can make it equals if you put in this universal constant of gravitation called G. It's a big G, all right? It's a big G. So you can put that in, and then you can have it in units like, yeah, what units would you get it in? What are units for the force of gravity on you? You always talk about it. People always talk about how much gravity's pulling on them, the force of gravity on them. And there are actually units for them that we use. You know what we use? Pounds. I mean, there are other units like newtons. Actually, there's a unit of Newton, of force, called the Newton. But we use pounds or lbs. Pounds, your weight, that's your weight. Your weight is the force of gravity on you. So you see that? Your weight is the force of gravity measured in pounds. Now, what about mass? Now, what about mass? What are mass units? Let's talk about mass units. Mass units. You've probably heard of some of them. Haven't you heard of grams? 1 gram is the mass of like a $1 bill. 1 gram. But if you have 1,000 grams, so you have mass units are grams. If you have 1,000 of them, you have kilograms. A kilogram is 1,000 grams. So 1,000 grams is a kilogram. What if you have 1/1000th of a gram? A lot of time medication is usually in units of these mass units. What about milligrams? So going this way, milligrams, like in medication, it's 1,000th of a gram. Now again, a gram is about the mass of it's a mass of a $1 bill, which you wouldn't even be able to tell you had in your hand just by, if you had 1 gram mass in your hand and you didn't feel it, you may not tell. But if you had 1,000 grams, a kilogram at Earth's surface is 2.2 pounds. 1 kilogram equals 2.2 pounds at the surface of the Earth. So let me show you this. Let me show you a weight here. Now, you're probably used to these things, right? I mean, you've seen these before. There. These iron plates, these weights. Now, look on here. There are 2 numbers written. Do you see the 2 numbers written? Do you see it says over here 3 pounds, 3 lb, and 1.4 kilograms? Well, guess what? Which one is the mass and which is the weight? The mass is the kilograms. Kilograms, 1.4 kilograms. And if you multiply 1.4 times 2.2, guess what you get? 3. Now, this is kind of weird. If you were to put this in space, if you were to put this mass in space, you know how much it would weigh? Nothing. Or if it were orbit around the Earth, it would be weightless. But do you know the 1.4 kilograms would be the same? So in reality, when the pounds are stamped on the weight, it's calibrated for the gravity at the surface of the Earth. If you were to take this to the moon, it would say 1.4 kilograms. That doesn't change. 1.4 kilograms, and it would say 0.5 pounds. So the kilograms, the mass stays the same, but the weight changes depending on the gravity, the gravitational field. So they assume when they make these weights that you'll be working out at the surface or near the surface of the Earth, and they're usually right. Yeah, most people don't work out on the moon. Yeah, there's nobody on the moon now. People don't work out. I mean, maybe they work out in the International Space Station. Yeah, in the International Space Station, something in orbit, you'd be weightless in something like that. There are ways to create artificial gravity. So there it is. That's something about mass and weight. All right, now let's talk about this. What if you wanted to lose or gain weight? Now, is it really weight that you're trying to lose or gain? Weight? Your weight is just how much gravity pulls you down. Guess what? You go into space, you're weightless. You don't have any weight. And so think about this. What if you travel to the top of a tall mountain? Let's make a mountain here. Do you see this? Look, here's a mountain. Kind of a crude mountain, but that's a mountain, kind of. And let's say you're at the top of a mountain, right here. That's you. Now let's see what's changed here. There's no mountain this tall on Earth. It would crumble under its own mass or weight. So now, what's changed here? Let's say the Earth didn't gain any mass, just kind of like a cotton candy mountain or something. Now your mass is the same. The Earth's mass is the same, but something's changed here. In this equation, something has changed, or this equation, something's changed. What's changed? Look at the distance here. It looks like it's twice as much as this. So you know what happens if this distance gets greater? If the denominator gets greater, doesn't the force, if this gets bigger and bigger and bigger, distance, doesn't this get less and less and less? If this were, guess what? If you weigh, let's say, 200 pounds at the surface of the Earth and go up to this mountain, you would weigh, if this is twice the distance, 2 squared would be 4. You would weigh 1/4 of 200, which would be 50 pounds. If you were, hey, you lost weight. You went from 250. But really, you're going to look the same because the mass is the same. So do you see weight and mass are not the same thing? Your weight changes depending on where you are. And your mass doesn't, unless you kind of lose an appendage or something. I don't recommend that. So really, yeah, if you want to gain or lose weight, you have to really, your distance doesn't affect you very much. You go up in an airplane, 25,000, 30,000 feet up, you'll be like a little bit less. You actually weigh 1/4 pound less, but you're the same mass. And if you lie flat on the ground, get really closer to the center of the Earth, you actually weigh a little bit more. So, if you want to gain weight quickly, you know what you can do? Lie on the ground. You lie on the ground, you gained a little weight. You're not going to be able to see that probably on a regular scale, but it's a tiny bit. Hey, you want to lose a little weight quickly? Go on a chair, stand on a chair. You've lost a little bit of weight, but really it's mass that you really want to change if you want to change your weight, if you want to gain or lose or lose weight. Now it's mass. It's not really weight. So now let's talk about things falling at the surface of the Earth, because things accelerate when they fall because of the force of gravity. So if you talk about, let's say, at the Earth's surface, if you drop something, now I don't know, look, I have a ball here. I don't know if you're going to see this. Watch. It's kind of hard to demonstrate, but it starts at 0 and it actually speeds up until it hits. What is the rate at it falls? It's called the acceleration due to gravity. And it equals 32 feet per second, because it's an acceleration. It's faster and faster. Remember, it's a change of velocity. It's getting faster and faster as it falls. 32 feet per second. Or if you, in other words, 9.8 meters per second, or per second squared. So something's increasing. So if something's falling at the Earth's surface or near the Earth's surface, after the first second of fall, it's going 32 feet per second or 9.8 meters per second. After the second of fall, it's going faster. It's going either 64 feet per second or 19.6 meters per second. So it's accelerating until it hits the ground and then it stops, right? But if it were not to hit the ground, that would be, it'd be kind of weird. Probably should hit something. Well, just keep going faster and faster. That's called the acceleration due to gravity. And that is also called 1g. I'd like you to know that. 1g. So if you experience 1g, you're experiencing the acceleration due to gravity at the Earth's surface. You're falling, you're feeling the gravity at the Earth's surface. Now, how do you feel more g's? You ever been in a roller coaster that kind of shoots you up or accelerates you and you're pushed back? You're feeling more you're feeling more G's. Now, so or in an elevator. Oh, think about this. Let's say you were in an elevator. This is kind of neat. And you're standing in an elevator. That's you, in an elevator, and it's being pulled up. If you were actually out in space in an elevator, or that's kind of weird, but like an elevator, like, yeah, like an elevator, little, I guess, what is it called? It's called an elevator. If you're out in space and someone's pulling you up or someone in direction at this rate, so someone keeps accelerating you at this rate, you know what it would feel like in that elevator? If you're out in the middle of the, like, you know, like away from anything that has really any gravity, if someone were accelerating you at this rate, it would feel like you're in Earth's gravity. So do you ever see movies, or actually you don't even have to see movies. You ever been in those things called like the gravitrons that spin around and you're pushed back against the wall? If it spins at the right rate, you could actually maybe stand up and walk on that wall kind of sideways, and it would feel like you're in Earth's gravity. First, in spaceships, the idea is a spaceship, so you don't have to be weightless. If it spins at a certain rate, and they showed this in the movie Interstellar, it's a pretty neat scene where they were playing baseball and trying to have a pop-up go from one side to the other, and then it did towards the end of the movie. If you're spinning in a spaceship, it spins, you can create like artificial gravity. It would feel like Earth's gravity. And you ever been in an elevator, even on Earth, where it actually starts moving up? Don't you feel a little heavier when it starts kind of going? And at the very, you ever jump in an elevator? I probably shouldn't tell you this, but I've had experiences like doing that, jumping, and you kind of feel heavy at first, but then when it starts slowing down, you kind of like almost hit the ceiling. Well, that's you're experiencing this acceleration, maybe either more acceleration due to gravity or a little bit less as you're jumping. So you're experiencing that. What about if you have your pasta in a strainer and it's filled like water? You just take your pasta out of the water and if there's all this water in it, what do? Now, don't you kind of like, here's what you do. I wouldn't recommend doing this with it. It's going to be flying out there to get the water out, but just kind of like pull it up a little bit. And if you ever try that, what you notice is that, don't you see the water kind of falling out the bottom more when you pull it up, you kind of jerk it up a little bit? Well, you know what you're creating? A little bit more G's for the pasta. From the pasta's point of view, it's feeling a little bit more gravity than normal. And from the water's point of view, it's feeling more gravity than normal. So guess what? The water's coming out. So try that. Try that at home. You don't have to do it now. But next time you make some sort of pasta, put it in that strainer, immediately go to the sink and do this. Yeah, don't do this like over the stove. And just kind of take the pasta and kind of pull it up a little bit. Take it in the strainer up and just look at the water falling out of the bottom when you do that. But don't kind of get wild with it and lose your pasta. Never want to lose your pasta. Don't do that. But just kind of like a little bit of like a up motion there, and you can see that water coming out. So now, what this means is that, we experience 1 G. If you were to experience like maybe 6 G's for a prolonged period, your body's really not used to that. Astronauts being, in rockets going up, like with the Apollo missions, I think they experienced like something like 3 G's, not too much. But there are actually roller coasters now where you're pushed back at like 5.5 G's, where you can feel, if you're pushed back with 5 G's, you know what that means? For that instant you're pushed back, it's like you're 5 times heavier. At 1 G, you're feeling like you normally feel. At 2 G's, you feel like you're weighing twice as much. At 3 G's, you're weighing 3 times as much. At 5 G's, you're weighing 5 times as much. So yeah, that'd be interesting to be on a planet, like working out, if you want to kind of get strong legs, to be on a planet that has, like 3 G's, and you'd weigh 3 times as much. Yeah, you wouldn't really have to do squats, just walk around for a while. And you get in pretty good shape. Your legs would. So interesting. I think it's really interesting. So that's kind of like what these G's are. So 1 G is the acceleration due to gravity. Now, what that means is after the first second of fall, an object falls 16 feet, which is, if you said 32 feet per second, 32 feet per second squared. If something starts, if you drop something, let's say this ball, and let's say I'm going to like slow motion, I let it go, it starts falling, all right? It starts falling and falling. Well, it starts out at 0, let's say, feet per second. After 1 second of fall, it's going 32 feet per second. If you were from 0 to 32, actually that distance, you kind of average from 0 to 32, it's 16 feet. In 1 second, it will have fallen 16 feet. So think about this. Something to think about. And here's what Newton thought about. The moon. Let's show Earth. Here's Earth. And let's show the moon. Falling. So here's moon. Moon. Here's Earth. Earth. Now watch this. The moon is a little farther away than we are at the Earth, at the surface of the Earth. So the moon doesn't feel quite as much gravity. So the moon fall is actually falling towards the Earth. It's falling not 16 feet per second, 1/20th of an inch in a second, in the first second. But you know what it's also doing? It's going this way at 2/3 of a mile per second. So you know what the net result is? The moon is falling towards the Earth, but it's also moving this way. So the net result is this. It's falling towards the Earth, falling towards the Earth, falling towards the Earth. But guess what? The fall towards the Earth, the Earth's curvature is the same as this path of the moon. It never gets to the Earth. It never gets there. What do we call this? That's an orbit. An orbit is a fall around something. There's only one force. It's actually gravity. Gravity is making it fall, but because of this tangential velocity to the side, it's going in orbit. Another way to see this, I'll show you another way to see it. So this is what Newton's thinking about, is the moon, and he's exactly right. Well, actually, I'll use this. You don't want to think, here's another way to think about it. Let's think about the Earth, and let's send, here's Earth. Earth. And let's have a mountain again. So there's a mountain. And let's just put you on the top of this mountain. I know it's a terrible looking mountain. It's okay, it doesn't matter. So here is you. Here is not, here is you. Here are you. No, here you are. That's you. All right. And what you're going to have, let's say, I don't know, let's say you're a pitcher and like, you have baseballs, all right? You have some baseballs with you, so you bring these baseballs up there and say, okay, you know, let's throw it, warm up, throw 50 miles an hour. So you throw 50 miles an hour and watch what happens. Oh man, falls. This falls to the earth. Nah, not very good. All right, pump it up to, I don't know, 70 miles an hour. Throw it out there and it still falls towards the earth. Okay. All right, your fastest speed, let's say 90 miles an hour. Oh, better. Nope, fell towards the earth. All right, doesn't seem to be working. So let's say you get a cannon, a baseball cannon, and you shoot the baseball at 5 miles a second. Now watch. Oh, a little bit better. All right. Pump it up to 6 miles a second. Ah, a little better. Pump it up to 7 miles a second. Watch out. Look at that. Aren't all of these baseballs falling towards the earth? But this one at a certain velocity never got to the earth because the curvature of this path of, they say, this orbit is the same as the curvature of the earth. So this is another way to look at it. So a object falling towards the earth at a certain speed is going to make it all the way around, and that is an orbit. So that's Newton, that's the law of gravity, and hopefully this made sense. So we'll talk to you next time.